After we're still going to stick with solvents and solutes. We're just going to kick her up a notch, add a little math in as well. So when we dissolve a solute in a solvent, this happens because there's collisions of the solvent particles with the solute particles. So every time we put some salt in some water, the salt particles are colliding with the water particles, and when we do that, we break up the salt into the Na plus ion and the Cl minus ion. So then what ends up happening is, remember, water is a polar molecule, and it has the oxygen and the hydrogens. Which part's partially negative, which part's partially positive? Good. So we have a negative here, positives on the hydrogens. So what happens is those collisions tear apart the positive negative attraction between the sodium and chlorine, and then the water molecules align themselves so that the partially negative oxygens are facing the partially positives sodiums, and then the partially positive hydrogens are aligned with the partially negative chlorines. Does that make sense? And so the water molecules are going to form this like force field around the positive and negative sodiums and chlorines. So there will be multiple water molecules around each of these ions from the salt. Does that kind of make sense? I know, I can't believe the announcements are still going either. So, increasing the rate or the intensity of the collisions between the solvents and the solutes will increase the rate of dissolving. So there's 3 ways to increase the rates of these collisions. We can stir or shake the solution, we can increase the temperature, or we can increase the surface area. All 3 of these things influence the rate at which something dissolves. So, looking at surface area, a solute only gets dissolved when its surface is in contact with the solvent. The more solute surface in contact with the solvent, the faster the solute will dissolve. So an example of this is a packet of sugar will dissolve then a sugar cube. It is a good thing to kind of have in your long-term memory is that many small particles will have a greater surface area than one large particle. It doesn't even matter what the particle is or what substance these are. This rule mathematically holds true for everything. Okay? The many small particles have a greater surface area than one large particle. So when we talk about dissolving, if we break up a substance into many small particles, it will dissolve faster than one single, like a sugar cube, will. Agitating the solution, stirring allows fresh solvent molecules to be in contact with more solute particles. Agitating can be shaking, stirring, dropping, whatever you can think of there. Temperature, heating the solvent increases the kinetic energy, so that means those particles are moving faster, and that more motion will equal more collisions, which then increases the rate of dissolving. We have a few different types of solutions. The first thing we need to look at is this concept of recrystallization, though. The recrystallization is the process of a dissolved solute returning to the solid state. This means when you put salt in the water, yeah, it will break apart, but if we're agitating it, sometimes those sodium and the chlorine ions will come back in contact with one another and reform that solid. So the rate of dissolving will equal the rate of recrystallization. The total amount of solute will stay the same. So if we look at this first equation right here, this represents your solid sodium chloride. Then you put it in the solution. We know it got put in the solution because of the AQ after it, but it remained as an NaCl compound. They didn't break apart. So that's showing that recrystallization is occurring. Does that make sense there? Okay. Then we also know this equation to be true. We can take solid salt and place it in the solution, and it will break into the ions. So what these equations have that are different is this double-headed arrow. And this is indicating that the solution, or that this reaction can occur moving this way, where you take the solid sodium chloride and just put it in the solution, and then it will also move the opposite direction. Is that that the sodium chloride will turn back to a solid instead of staying in solution. So this second equation, the one where we have the actual ions, is a more factual or actual representation of a solute dissolving in a solvent, because yeah, it will break apart because it's got the double-headed arrow, so we're moving to the right. But we also know that recrystallization happens, and moving to the left shows the recrystallization process. Does that make sense in these equations? So which equation, 1 or 2, is the more acceptable representation of dissolving a solute? 2, because we have the dissociation, which yes is happening, but we also have recrystallization going on. And so this dissolving and recrystallization, dissociation and recrystallization is happening simultaneously. And a solution equilibrium will occur, so that means the rate of recrystallization and the rate of dissociation will be same eventually. And when that happens, we have reached the solution equilibrium. They're occurring at the same rate. One is not happening faster than the other. Okay? It does not mean we have an equal amount of recrystallized solute particles as an equal amount of dissociated ions. Okay? It means the rate of these processes is equal. Not the concentration, not the amount. It's the rate of the processes. So this is the key here. Yep. So that brings up saturated and unsaturated solutions. A saturated solution is a solution that contains the maximum amount of solute that is capable of being dissolved. I think this is where our brains actually get to see the amount of sugar particles or salt particles. Here we are dealing with an actual quantity of a substance. And so there's a mathematical formula we'll look at here in a little bit. And then an unsaturated solution is where your solvent can still hold more solute. Temperature is a key factor in this. So in order to compare these two situations, the temperature has to be the same between both situations. So here we have 30 grams of salt in 100 milliliters of water, and the solution is unsaturated. We know that because there's no particles left. So that's usually a pretty good indication that there's still room in between the water molecules to hold more salt. Here, since we upped it to 40 grams of salt, kept the water quantity the same and the temperature the same, and we can see that there is a little bit of the salt left. That means there's no more room in between the water molecules to hold any more salt ions. Okay, so they cannot dissolve. So they're just going to sit there. That's when we know we have a saturated solution. It's full. Can't hold any more. Does that make sense on that? Kind of a way to think about this would be like a Kool-Aid solution. If you have really an unsaturated solution, there's not much sugar in it, it doesn't taste very good. Whereas if you have a saturated Kool-Aid solution, it's probably super sugary, probably even more sugary than most people like to have because it's got a lot of sugar. There's a lot more sugar in it than necessary. A supersaturated solution is a solution that contains more than the maximum solute than is being capable of being dissolved at a given temperature. This will only occur if recrystallization does not happen very easily. To do this, you have to dissolve the solute at a very high temperature, and as it cools, recrystallization should occur, but it doesn't. So we kind of gave, what this situation is describing is we kind of gave the solution a jump start by heating it. If you heat a solution, it should hold more solute. The only thing that that's not true for is gases, and we'll talk about that in a couple slides. And so by jump starting the solution, by heating it, we've allowed it to dissolve more than it should normally hold. And as we cool it, most solutions will form through the recrystallization process very rapidly because the cooling has happened. And you might actually see some extra particles then. But in a supersaturated solution, the recrystallization will not happen. And so, excuse me, those extra solute particles that dissolved at that high temperature will still be dissolved. Does that make sense? Questions? Okay, Marta? All right, solubility values. Solubility is the amount of a substance that is required in order to form a saturated solution in a given amount of solvent at a specific temperature. Again, temperature is important. Let's see. For gases, we have to look at the temperature as well as the pressure. Your general formula for this, mind you, I'm saying general formula, is you look at the grams of solute over 100 grams of solvent. And there is a table in your book, table 16.2, that will become your friend because it shows you the solubility of solutes at different temperatures. So there's some good information there. An example of a solubility number is that for sodium chloride, NaCl's solubility will equal 36 grams of NaCl per 100 grams of water at 20 degrees Celsius. So for reference, 23 degrees Celsius is what my classroom is at. So it's just a titch colder than room temperature. And so we have the grams of the solute, NaCl, over the grams of the solvent. Now, if NaCl or table salt were being dissolved in rubbing alcohol, the 36 grams may not hold true. Okay? This is very dependent on the solute and the solvent and the temperature. Okay? It will change. Your solubility will change if the solute changes, if the solvent changes, or if the temperature changes. That brings about these solubility curves. I like this graph. It is very informative. So, first of all, it looks at temperature on the x-axis and it grams of solute over 100 grams of water. So this is telling us that water is the solvent. If we had questions dealing with a different solvent, we could not use this specific graph. And so your book assumes that water is the solvent unless otherwise stated. So when you're going through doing problems and questions, if it doesn't say what the solvent is, you are safe to assume it is water. Okay? So for most solids, solubility will increase as temperature increases. That means water will hold more of the solute when we increase the temperature. However, if you look at sodium chloride's line, which is down here, what do you notice as temperature is increasing? Does the solubility increase, decrease, or stay the same? It stays about the same. So what does that tell us about the solubility of NaCl? It doesn't really change with temperature. It's one of those solids that temperature doesn't really affect solubility. We could just say, if you want to write something, temperature doesn't affect or effect? I think so too. Affect NaCl's solubility. Then if we look at HCl's line, which is right here, HCl, NH3, and SO2, what do you notice is their solubility trend as the temperature is increasing? Yeah, so their solubility is decreasing as temperature is increasing. Why would that be? Or what could you hypothesize about those three compounds? Are they solids, liquids, or gases? They're gases. So remember that with gases, the solubility will decrease if temperature increases. If temperature decreases, your solubility increases. Okay, so they're the one that gases are the opposite of the solids and liquids. Let's see. Pressure only really affects gases. Gas solubility will increase as the pressure above the liquid increases. So I kind of think of it as like when you pack to go on a long trip and you're trying to jam as much as you can in a suitcase and you have to sit on it to get the zipper closed. Think of that as like with the gases. If you sit on it, you're applying more pressure so you can shove more stuff into the suitcase. Does that kind of make sense? And another way to think about it too, another kind of real life analogy is a can of soda pop, whatever you want to call it, has a gas dissolved in it, that carbon dioxide, the bubbles, and as soon as you open it, you hear it, psst, right? You have decreased the pressure and you are therefore releasing the gas bubbles out and the solubility has decreased. Does that make sense there? So solubility will increase as pressure increases. We get a nice fun mathematical relationship called Henry's Law that shows you the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the liquid. We can put that nice little ratio into practice. S for solubility and P for pressure, by the way. The solubility of a certain gas in water is 0.745 grams per liter at standard pressure. What is the solubility when the pressure of the gas present above the solution is raised to 4.5 atmosphere? The temperature is constant at 20 degrees Celsius. That is a key piece. You cannot use this ratio if the temperature changes. The temperature has to stay the same, otherwise the ratio does not hold. So, things we know, your initial solubility is 0.745 grams per liter. Your initial pressure is at standard pressure, which is what? 1 atmosphere. Why did we go atmosphere on this one and not millimeters of mercury?
Because the next one given is
Yeah, the next one given is an atmosphere. So our second pressure is 4.5 atm. And it is asking for us to solve for the second solubility. So, looking at the pressures, should the second solubility value be higher than 0.745 or lower than 0.745? It should be higher because with an increase of pressure, we increase solubility. So the formula S1 over P1 equals S2 over P2, and then plug them in. 0.745 over 1 equals S2 over 4.5. I do the cross multiply. That gets us 3.3525 atmospheres equals S1, which would be multiplied by 1. And did our solubility increase?
Yes.
So does our answer make sense?
Yes.
It sure does.